Hello and welcome. My name is Leandro Avila. I work at the Julis Research Center. In this video, I will talk about the essential of large-scale models and how those tools help us to understand and manage water resources across river basins, countries, or even continents. By the end of this video, you will understand what large-scale models are and why they are important for water resources management. Examples and application of some large-scale models and output obtained from large-scale model applied over Europe. This video is designed for water resources planners, policymakers, and environmental professionals. Water resources face increasing stress due to climate change and population growth. To deal with those challenges, we need tools that can assess future scenarios and evaluate the impacts associated with climate change. In a nutshell, hydrological models are a mathematical representation of the water cycle. They can be categorized by their complexity, from empirical using a statistical relationship, conceptual using simplified physical concepts, and physical models which solve physical equations. The accuracy of those models can be improved by using two different approaches such as calibration and data assimilation. A calibration process is performed by tuning parameters to match historical data, like river flow. However, for pure physical models, data assimilation is performed, which is a common process that continuously updates the model internal states, like soil moisture or snowpack, by integrated satellite information and in situ observation. In the Star4Water project, we worked with a set of open source models. For example, the LISFLOOD model is an operational implementation for flood forecasting, and it is the core model used by the European Flood Awareness System. The Wflow SBN is a distributed hydrological model that is coupled with a simplified groundwater representation, and it's excellent for analyzing the terrestrial part of the hydrological cycle. The Parflow-CLM is ideal for simulating complex, variable saturated groundwater flow and overland flow. It's particularly powerful for analyzing the interaction between the subsurface and the land surface flow. The Community Land Model, or CLM, simulates a wide range of biophysical and biochemical processes. It's primarily used for studying land-atmosphere interactions. The Terrestrial System Modeling Platform, or TSMP, is a highly advanced group of models that integrate the atmosphere, land surface, and subsurface hydrological processes. This system was designed to analyze complex environmental feedbacks, for example, how the groundwater level can influence evaporation and local rainfall patterns. Looking at the specific setup of each model, the LISFLOOD was implemented by the Joint Research Center. This is the pan-European operational benchmark running at a high resolution of 0.0166 degrees from 1993 to the present day. A Wflow SBN was set up by Deltares. It also covered Europe at a high resolution of 30 arcseconds from 1990 to 2022, primarily focusing on simulated river discharge. The Parflow-CLM model was implemented over Germany by the Juris Research Center at a spatial resolution of 600 meters. This setup produced detailed outputs like soil moisture and water table depth. The CLM model was also implemented by the Julis Research Center. It runs over Europe at a resolution of 0.0275 degrees from 1995 to 2018. And finally, the TSMP model was also implemented by the Julis Research Center across all Europe at a resolution of 0.11 degrees from 1996 to 2017. For those models, we benchmark different simulated variables like river discharge, soil moisture, snow water equivalent, evapotranspiration, and in some cases, water table depth. We can find some real application of the previous models. For example, the LISFLOOD model is used as the core hydrological engine of the European Flood Awareness System. It provides pan-European flood guidance and early warning products up to 10 days in advance for national hydrological services. Another application we find with the Parflow model, which is used as part of the adapter project Wasser Monitor, a platform producing operational deterministic water sources forecast. The model simulates 3D variable saturated subsurface flow, providing a fundamental process-based view of drought development, moving beyond simple soil moisture indexes. In Star4Water project, we performed a benchmark between the presented models. Here I show you quick results we obtained. Our analysis for river discharge, validated against a network of in-situ observation, reveals a clear spatial pattern in model performance quantified by the KGE metric. In general, the model presents better performance in Central Europe, in contrast with regions which are dominated with snow melting process, which present lower performances. Another variable included in the benchmark is snow water equivalent. In this case, we observed some examples. For example, minor difference between the observation and simulation are also minor difference between the calibrated models like LISFLOOD and pure physical models like CLM and TSMP. Those results help us to quantify uncertainties associated to multiple large-scale models and allow us to implement strategies to mitigate impacts associated to climate change in specific regions. Some large points about this video are that large-scale models are essential tools to provide a physical consistent representation of the water cycle over large domain, including river basin or continents, allowing us to explore impacts associated with different climate and socioeconomic scenarios. By benchmarking the set of large-scale models, we can quantify uncertainties associated with the estimation of hydrological variables that are important for water resources management. Looking ahead, the benchmark gives a way to integrate hydrological models with machine learning models, for example. While physical models provide foundation laws, machine learning models can be used to emulate those results, reducing computational cost and be a flexible tool for predicting hydrological variables. The Star4Water provides the platform, tools, and the validated performance data to move these models from research into practice, supporting evidence-based policy for a more resilient water future. Future reading and training material are available in the Star4Water Academy website. If you have questions or comments, please contact us through our website. Thank you very much.